Let's take a look at other forms of chemical equations we can write for precipitation reactions, as well as some other reactions, but we're just going to take a look at it for precipitation reactions. And these are the molecular, complete ionic, and net ionic equations. So let's take a look at each piece by piece. We'll start off with the molecular. And in the molecular equation, we write everything as compounds. And the molecular equation is most useful because it's going to be what tells you what you need to pull off the shelf, right? So for example, what we're going to do here is we're going to take our silver nitrate, which is an aqueous solution, combine it with our sodium chloride, which is an aqueous solution, to form silver chloride, which is a solid. So this is a precipitation reaction, and some sodium nitrate, which is aqueous as well. And our equation here is indeed balanced. So that's our what's known as our molecular equation. We write everything as a compound. Next up is our complete ionic equation. So we're going to write here we're going to write everything as ions. Now we'll say write aqueous solutions as ions. And what this one does is it gives us the most realistic picture of what's actually happening on a molecular level. For example, the silver nitrate is an aqueous solution. So when you put that into water, it doesn't really exist as silver nitrate anymore. It exists as silver ions floating around in solution and nitrate ions floating around in solution, but they're no longer really chemically bonded to one another. So that's what we're going to demonstrate through the use of this complete ionic equation. So we're going to write it as silver plus as an aqueous solution, plus NO3 minus as being aqueous, plus the sodium plus as aqueous, right, from our sodium chloride, and then the Cl minus as aqueous. And what that's going to give us is our Na plus still as aqueous, right, from this sodium nitrate that's still aqueous, and NO3 minus that's still aqueous. And then finally, AgCl. We're going to keep this together because now it's a solid, and so it is indeed chemically bonded to one another, right? And so the complete ionic gives you the most realistic picture of what's happening in solution, right? In our solution, we have these four ions mixed together, and then they transform into this solid, which is chemically bonded to one another, and then these ions, which are just floating around in solution. All right, and then finally, we have the net ionic equation. And what we're going to do with the net ionic equations is we're going to get rid of spectator ions. And what the net ionic equation is going to do is it's going to tell us what is actually happening. In terms of the chemistry. So what's a spectator ion? A spectator ion, as the name implies, is something that's just watching the chemical reaction occur, but it itself is not participating in that chemical reaction. And so they're going to be things that show up on the left side of our chemical equation and the right side of our chemical equation as the same exact thing. So for example, this nitrate shows up on the left side and as the right side as NO3 minus in aqueous solution. It was there in the beginning, it was there at the end. It didn't actually do anything. All it did was watch the reaction. Same thing with this sodium. It appears the same on the left side and the right side, so we're going to cancel them out. And then we see what's actually going on in our equation. What's going on in our chemical reaction here is that we have silver plus ions interacting with chloride ions to form ionic bonds and form a solid clump of silver chloride. So there are three types of equations: molecular, complete ionic, and net ionic equations. Honestly, I don't think it's the most important fact, but we'll do a little question here and there about it.